Today we are working with regular polyhedra. Last section, 14.4. A better name for regular polyhedra is platonic solids, but the more technical term is regular polyhedra. So a polyhedra is any multi-sided closed figure, and a regular polyhedron is one in which each of the faces, including the base, are congruent and regular. And so, to have a regular polyhedra, you need each face to be the same shape. An equilateral triangle, a square, a pentagon, for example. And each of those shapes need to fold together to make our three-dimensional figure. Consider this figure here on the left. You see the T. If you were to fold up each of these squares along the vertex, you could create a cube. We have already seen a different regular polyhedra as well in problem 14.10. That was the tetrahedron, made up entirely of equilateral triangles. Made up of 4 equilateral triangles. So let's take this equilateral triangle and make 4 of them. And here we are. This shape, when folded up, I can fold these outside vertices into directly over the center of the central triangle and make a tetrahedron. So using triangles, squares, and pentagons, what are the other polyhedra we can make? Can we make one using 6 squares? Yes, we've already done that. One, two, three, four, 5. Oh, I'm making a mistake. Let's see. The sides, the roof. Oh, I need to add another square here. And now that could be folded. We'd have the base, 2 side faces, the front facing side, the top, and the back side of this cube. Can we use 8 equilateral triangles to make a solid? Let's try that. Let me see that. To do an 8-sided figure, I would do this. I would make a tetrahedron, and then I would make another tetrahedron, and I would connect them to each other at the base. I put those 2 bottom faces together. If you look at this figure here, you might realize that you could fold it in such a way that you would get an 8-sided figure out of it. Take a moment to look at it and contemplate how to fold it into an 8-sided figure. If I were using pentagons and folding those, how many sides would my figure have? I've drawn the beginnings of the polyhedron here. I have 3 pentagons around this one point. So I could fold along each of these edges, this edge and this edge, until these two edges met. How many more faces could I fit in this figure? The answer is 9 more faces, 12 total. A pentagon can be folded into a 12-sided figure. We call a 12-sided polyhedron a dodecahedron. Do for duo, deca for 10. Dodecahedron, 2 and 10 hedron, also known as 12-hedron. And a hedra is just a Greek word for face or side of a figure. So don't let the word hedra intimidate you. Poly means many, hedra means faces, so many faces. Dodecahedron, 2 and 10 faces. Tetrahedron was 4 faces. Here you have a representation of all 5 Platonic solids. Let's talk about the parts of these solids. We have vertices, we have edges, and we have faces. And if there's a bottom face and a top face, we will call those bases. Those are the base faces, if you will. The names of these polyhedra are the tetrahedra, the 4-faced guy, the octahedra, 8-faced, the cube, the dodecahedra, the 12-faced person, and the hardest one to remember, the icosahedron, which has 20 faces and is made up of triangles. In problem 14.12, we are given an octahedron. The first thing we are asked to do is find BD. So to find BD, maybe the first thing to consider is what plane is BD on. It's on a plane within a shape, and that shape is BEDC. What shape is BEDC? If you were to look at it from above, directly above, what shape would it be? It would be a square. And so to find BD, we're finding the diagonal of a square. We know that AB is 4, and therefore all of these other edges are 4. So this is 4, it's a 4 by 4 square. What's the diagonal of a 4 by 4 square? Ooh, the gears are turning. It's an isosceles triangle. 4 square root of 2. Okay, our next step is to find AF, from A down to F. Once again, this might look daunting because you haven't found anything like this before. We're dealing in 3 dimensions, it's looking tough. But remember, we just take everything we see and we turn it into right triangles. That's the story of geometry. We've already found in a previous problem from A to the point in the middle, we'll call it O. And we know from O to F is going to be the same distance. So let's write this equation as AF over 2 equals AO. And how would we find AF over 2? How do we find AO? Well, we would make ourselves a right triangle with AOB. And that would give us an hypotenuse of AB. And we already know what BO is because it's half of BD. You see why we found BD first? Very clever. So that means 16 minus BO, which is 2 root 2, squared. And I want to just do the squaring together because I know you all feel uncomfortable dealing with exponents and square roots. So square root of 2 times square root of 2 is 2. And 2 times 2 is 4. So 4 times 2 is 8. 16 minus 8. Now 8 can be simplified to 2 root 2. So we have found AO. What's AF going to be? It's just going to be 2 AOs. So AF equals 4 root 2. And now our last question, and now our second to last question is find the area of BCDE. Well, that's a square. We know how to find the area of a square. Four times 4 is 16. And that's only going to give us half of our volume. So we need to multiply that whole thing by 2. Reduce that down on your own, and you will have completed 14.12. Congratulations.